for graduate school because I saw how many amazing actual microchips there are made, right? So not just theory, I mean, a lot of amazing research groups have put out papers where it's just theory and calculations. Every single paper that comes out of the UCSB research groups has an actual microchip they made, brand new, and I was like, wow, that's the place I want to go. I mean, that's why I'm here. And
I'm sorry, what's your name again?
Demis John. So let me do a quick introduction here. I'll do a quick intro here. So that's what we're talking about here today. So yeah, my name is Demis. We're going to talk about micro nanotech on the Central Coast, specifically in town. And some of you work at companies that know know how much microchips how many microchip companies we have in town. I'm really hoping that you leave here realizing that we live in a place that makes the most advanced microchips of 20, 30 different types. And it's really amazing if you're into this kind of thing and if you like actually making physical hardware. So yeah, about me. I did come to UCSB in 2005 with my lovely wife Azita here. And that was about 5 years before you existed, Jacob. And I came, like I said, because all the research papers I was seeing coming out of this university actually had physical microchips they had actually made by hand in their clean room, and they were solving cutting-edge problems, right? So, for example, this I started in Dan Blumenthal's research group, worked really closely with John Bowers' research group. This is an example of one of the early chips that I was working on. This is a 40 gigahertz, 40 gigabit per second. Think of 40 gigahertz, 10 times faster than your typical computer chip. Optical chip, right? And these kind of chips are the reasons that your internet got 100x faster without you paying more per month. All transparent, all happens, you know, over behind Cox over on Fairview. None of us see it, and yet everything got faster. This is the kind of technology that actually enables that, right? Started with these kind of chips, really high complexity at the time. This was the most complicated, highest number of components on a photonic chip ever made at the university. Very quickly, you know, a couple of big companies in the Bay Area actually superseded that. But again, like really cutting edge, advanced photonics. Running chips that run on light. And then I actually graduated on this particular chip. This is on my phone. I have pictures of this everywhere because it's a really cool picture. And I'm very proud that I graduated. And that's the chip that did it for me. But we made the lowest loss glass waveguides, meaning instead of a wire that transmits electricity, waveguides are basically the wire that transmit light. We made those, that held the record for about 7 years. They started beating it about 2 years ago. So, so just to give you an example, this is the kind of stuff I'm a geek for: lasers, fiber optics, photonics. But really, I love making microchips. And now I work at the UCSB NanoFab, which is the place I did my graduate work in, and worked for 5 years at a local company, also making extremely cutting-edge chips. I'm going to show you some of those as well. And now I actually work for the UCSB NanoFab, helping everyone make all their microchips. So sort of like being, if we have a resident, you know, hackerspace guru here. Is there one here? Who here is the hackerspace guru?
I think there's a few of us.
One of you? Okay. So I'm like that for the microchip lab, right? So I'm helping people make all sorts of different microchips. So some of what I'm going to show you today is actually the different microchips made in town. Hopefully you recognize some of these companies. Probably some of these you've driven by and you're like, I always wondered what happened in there. I'm going to try and show you what they actually do. So just to give you a quick overview, at the UCSB NanoFab, so that's at on campus, I went through. It's an open access lab, and anybody can go in there and use it. Sort of like this, except it'll cost you, if you're at a company, it'll cost you $150 an hour, right? So it's a little bit more expensive than your typical 3D printer. I'll talk about why you would go there or why you wouldn't go there. But I took all of our database of all the users that had used the NanoFab for many years, and down selected it just to companies that had used our NanoFab. These are photographs that I took from inside. Also, companies that are only in Santa Barbara and Goleta and use it only within these 2 years. I could update this, I guess, run some more numbers. And just in that case, just companies that call Santa Barbara and Goleta their headquarters, we have 29 companies. And that was in 2018. I personally know at least 5 to 7 startups that have started since 2020. So we have a lot of startups that literally make cutting-edge microchips that no one else makes in town. Okay, so a little bit more data here. For people that are in the photonics community, this area has the name Infrared Valley, going all the way back to Howard Hughes Research Labs, which now Raytheon bought them. So that lab used to be Howard Hughes. So back in the 50s, when they first started making infrared cameras for post-World War II, Cold War era type of, looking for ICBMs before, that are Star Wars, Reagan Star Wars program, that kind of stuff. This is, again, just a smattering of local companies, large and small. You work at a very large company, but actually some of these companies, like for example, even the company you work at Northrop Grumman, many of those companies started as small companies. I think that one was Orbital ATK probably first, and then got bought by a massive company, Northrop Grumman. So a large number of these large companies here actually were small groups here that got started and then got acquired by a large company, and they added that to their portfolio. That's true for, like I said, Raytheon bought Howard Hughes, but same for Teledyne FLIR on Hollister. That used to be Indigo way back in the day. So a lot of the large companies in town actually were small companies, and they still retained their sort of small group Santa Barbara feel to it, if that makes sense. So this really is, if this should tell you anything, this really is an innovation hub for microchips. Many different types of microchips. Specifically, many of these are chips that run on light, so infrared cameras, infrared lasers, blue LEDs, blue lasers, that kind of thing. But also you're going to see a couple of others. I'm just going to kind of quickly run through some of the different companies that we see in town that, again, just kind of, I want you guys to, a lot of people, this is what's funny about this, that me and other people who came here for graduate school or came here for jobs may have already known that there were this many companies that did amazing cutting edge stuff here, or just knew that there was cutting edge microchips here. But a lot of people who have grown up here have no idea about that. And I really want to make sure people who live here, maybe are going to school here or are kids here, right? And I really want them to be able to, know that this is a hub for this kind of high tech. And so that's, 5% of people who get excited about and want to actually get into those fields, they got to know that when they're in like 6th to 8th grade, so that they then take the right classes and take the right, decide whether to go to college or whatever. I really want people who live here and live in this area all the way from Ventura out to Santa Maria to know about this so that we can actually start hiring local people. And part of that is that most of the high-tech companies here really struggle to find enough people that get excited about this, want to make stuff, want to get in there and actually see things work. I think it's definitely a win-win for the companies and for local people if we can make sure people who already live here get excited about this kind of technology that we do in our town. So just some numbers. The NanoFab itself, again, being open access. These are some maps that kind of show where people have come from that accessed our lab. Okay, so obviously a large number of local users. Our lab actually hosts about 50% companies, many of which are local, not all, and 50% researchers. So I think it's about 40-60. So 60% of those people are graduate students working for professors at UCSB, but about 40% of those are actually all companies that use our lab. So it's really busy lab. I could go in there right now and I'll probably see about 10 people in the lab right now. Even on a Saturday, you'll see people in there. It's a really busy lab, which is we have very, very high usage compared to many other university labs. And again, you can see here, 68 companies local to Goleta and Santa Barbara. This is going back all the way to 2006, so not all of those exist anymore, right? But just to give you an idea, right? And 29 of them started by UCSB faculty or graduate students, or graduates from UCSB. Sometimes graduate students, sometimes undergraduates, okay? So again, just to give you a picture, this area has a really great entrepreneurial culture and ecosystem, right? People can come up with an idea. They can come to the lab without having to build a multi-million-dollar facility and just try out their new microchips. And there's venture capital in town, and there's entrepreneurial training, there's incubators. Like, we really have an amazing ecosystem for starting companies in this kind of high-tech field. Let me also say, please feel free to just raise your hand if you have any questions. I don't think there's any such thing as dumb questions, because this stuff is really complicated. So please do ask questions and just go ahead and interrupt. I'm perfectly happy. Yeah.
You guys do organize tours in the actual lab?
I do, yeah. Yeah, absolutely. I'm happy to do that.
Yeah, but we also need to.
I gave 2 yesterday. We gave another one today. So yeah, just you can grab my card afterwards or grab my email address. It was on that first slide. And yeah, hit me up. Well, I'm happy to bring a couple of people and give them tours. Raise your hand if you've gotten a tour of the NanoFab already. Okay, everyone in my family, Mike, Will. Again, just like a smattering of like the companies that have used our lab. The bold ones are kind of our local companies. Again, just it's kind of overwhelming how many companies have incubated by being able to just pay hourly to use an expensive facility like that. Here's a little bit more deep dive into some of those companies. Anyone here ever heard of Google? Raise your hand if you heard of Google. Okay, good. Anyone heard of Google AI? Okay, not everybody. This is a quantum computing group. They made their first quantum computing. They actually effectively, there was actually a research group at UCSB that Google worked with and then basically hired everyone from the research group to launch this whole effort. Google now has, what, 3 or 4 buildings in town. One of them is a fab. So they made their first chips in our lab. They still use our lab, but now they make their own chips going to much higher yields and many more qubits than they made in our lab. And that is the quantum computing hub of the entire Google network. People are doing quantum computations on the computers behind Cottage Hospital right now. They have 6 or 7, something like that. This company is from Camarillo, incubated in our lab, was the biggest user of our lab for something like 6-7 years, and then we helped them transfer all of that, and they built their own lab down in Camarillo. These guys are actually, they used to be right on Pine Ave, if I remember correctly, right next to the UPS, making flashlights that can shine 2 kilometers. I mean, that's really hard to do for search and rescue and things. I'm not going to go through all of these, but again, actually, the truth is I know the details of all these companies, a lot of what all their devices work, how their devices work, what the applications are, how the microchips work. So happy to tell you more about it. But just to give you an idea, each one of these companies does something totally different, and nobody else really does that. That's why they started, and that's why they exist, and they were able to incubate that in town. So to dive in a little bit deeper, one thing that Jacob found out by going to chess club in IV was that Raytheon Vision Systems right here on Hollister actually made one of the detectors on the James Webb Space Telescope. Raise your hand if you've heard of the James Webb Space Telescope. Okay, just about everyone here. If you haven't heard about it, it's basically the biggest world project telescope that's floating in space right now, taking the most unbelievable pictures of the universe, higher resolution than any other telescope that ever existed. Has, if I remember correctly, 3 different detectors, 3 different cameras on it, one of which was made right here in Hollister. Okay, so think about this. This is, an ESA, a European Space Agency, and NASA project. I mean, it's really a global level project. And how many companies in the world could even possibly be contracted to do that? One of them's right here in Goleta, right? The other one was made, one of the other ones was made at Teledyne in Thousand Oaks. So again, not very far from us. And then the last one was made in Arizona, if I remember correctly. And then it might also have a visible camera. Those are all infrared cameras, by the way. I believe so, yeah. I think that's correct. Okay, this company currently has infrared cameras on the Mars rovers right now. If we go again, a number of these are infrared, not all of them. There are 2 companies in the world that make infrared cameras that actually fit on your smartphone. When I was in graduate school, we had these big infrared cameras. They were like $50,000, and they were super slow and really not very good. And FLIR, and this is actually a spin-off from this Seek Thermal, a spin-off from the same company, both in town here. Both those companies are here in town. And they dropped the price of the infrared camera from $50,000 in giant to smartphone capable and $200, right? So now every firefighter can have one. Every search and rescue or policeman can have one, right? So if they're out fighting fires and they want to look for hot spots in the weeds, right? This is how they do it, right? So it suddenly became accessible to everybody. Remarkable. That's right here in town. So if you ever wonder what Teledyne FLIR right on Hollister that has that huge building kind of just past Target and between Los Carneros and Target, that's just one of the many things they do here is they make these there. Okay, only 2 companies in the world that make that. Lockheed Martin, you've probably, I don't know if you know where this is. This is behind Target. They have a clean room there. Also makes infrared cameras. And let's see if I can. I got some videos here. Let me see if I can get that to play. Never mind. I won't. I'll skip it. Do you want to see if you can maybe hit play on this one for me? Maybe you have to click on it. I don't know how to do that from this pointer. Thank you. So, and then you can also hit play on this one as well, the one on the bottom too. So you can see that they do, defense applications, as well as this hummingbird. Oh, sorry about that. I'm messing up your pointer there. This hummingbird video is actually really interesting, right? Because like I said, I used infrared cameras in my graduate school, and they were big and super slow. So if I moved the thing I was looking at, I'd literally have to sit there and count 20 seconds for the ghost image to stop moving and show me what I was looking at. So the ability to take an infrared image of a hummingbird's wings, actually a really big deal. That is really hard to do. And this is these are all, by the way, public things you can find on their websites. This is an example of the actual infrared detector, right? That's an array of, I don't know, a couple thousand by thousand pixels of infrared pixels. They make those chips here. If you go behind Target, you'll see the big liquid nitrogen tanks. Anytime you see a giant liquid nitrogen tank, probably a clean room there, probably a semiconductor machine shop. If you don't mind hitting play on these ones for me, thank you so much, Mike. Appreciate that. This is a company I used to work for called Pravium Research, making tunable lasers. Turns out if you make a really fast and wide-range tunable lasers, there's all sorts of cool things you can do with that, one of which includes taking 3D images of the eye. If you hit play on the one on the right as well, they also were able to, this is even before LiDAR became like a common term that everybody knew for self-driving cars. But that image on the right is a volumetric 3D image of a cubic meter, 1 meter cubed, right? With 16 micrometer resolution. Okay? It turns out that the vast majority, this was like a 4 terabyte file of mostly zeros, because you're saving all the zeros where the light didn't hit anything. So just to give you an example, like that's incredibly high resolution, and nobody had really ever done that before. It's enabled by the lasers that Pravium makes. This is an example of the color, the width of the different colors that their laser can span. Here's a picture of what their actual chips look like. Again, this is all public information, right? So the laser itself is actually only a 0.5 millimeter wide little block, okay? That is also true for the laser pointers in all of any laser pointer. It's also true of the LEDs in your house. We'll look at that in a second, right? But you look at the complexity, right? Like, look how small those features are. This is actually a very, very fun and complicated device. It's got mechanical arms with an air gap that vibrate. It's got electrical tuning. It's got light being trapped back and forth and electricity going into it. Really, really sophisticated. Really fun to work on. So a 0.5 millimeter wide. We're literally talking the size of a grain of sand. But is the thing that enables these kind of pictures. Without that, they can't take those kind of 3D images. To be fair, there's a whole other complexity on putting together the system and imaging someone's eye fast, right? There's a lot of electronics going and other optics going on there, but this is one of the enabling components made here in town. Google Quantum AI, as I mentioned, this was actually they were the first group to claim quantum supremacy. Anyone here ever heard of quantum supremacy? Ever heard of that? That was a term that I guess it kind of went away after they did in 2019, because it was the idea that a quantum computer could compute something that a regular computer couldn't do. So if I remember correctly, from their paper that came out in 2019, November or December 2019, their quantum computer could compute a very specific quantum calculation, right? We're not talking 2 + 2 = 4. A very specific, complicated algorithm. They could do it in 6 seconds, whereas a regular computer would have taken 600 years. Okay, so it enables you to actually do computations you couldn't do before. And again, this is now a big effort here. I think I recently heard they're going to build a new fab here in town soon. These are the actual qubits. These are from their papers, and this is kind of what the circuit looks like. These are superconducting qubits. So whole other complexity. You can make the chips, but then you've got to cool it down to 4 Kelvin, get electricity in and out without heating it up. I don't even know how you do that. There's a whole other expertise there. Another thing that's really big here, especially at UCSB, and we had, again, a number of the startups that came out here actually work on these kind of technologies, is LEDs. Who here remembers when you did not have LED light bulbs in your house? When there were those little metal wires, right? That's what they were. They were a little metal wire in a little mini vacuum chamber, right? That's what they were.
What were the little mix tubes?
Yeah, I've seen those. Those are cool. Now, raise your hand if you have LED light bulbs in your house. All of us, right? So I think that's really interesting, right? Because Azitha will remember when I knew that people worked on, I have friends that worked on this. They literally gave me the LEDs they made by hand, and the colors weren't good enough. They were too blue. I remember I got super excited about putting an LED light bulb in our house, and I didn't tell her I just changed one of them. Was really excited that there were LED light bulbs in Home Depot. You remember what you said? Yeah. She's like, "Did you change that light bulb?" I'm like, yes. Can you take it out? Like it's flickering, it's blue. Like she hated how it looked. It was like another 4 years before they were warm color enough. They didn't flicker. I mean, it was a lot of research, and our friend Stuart actually literally was working on the color of the LEDs. It took for years before they actually were good enough that people would actually buy them. LEDs are a great example, right? Because all of you have them in your house. Actually, could have brought some for you. But here's an example. Although they say they last 10 years, do they actually last 10 years? A bunch of them, I have a bunch that died. It turns out it's not the LED that died. Okay, fine, the LED probably lasts 10 years, but the electronics in the base actually die long before that. But so I had the dead one that I cut open. So here you can see the individual LEDs, those are the yellow phosphors. And this is an example of what they look like when you've actually brought them out of the fab, right? So what used to be a little metal filament, mechanically produced, goes all the way back to Edison, has now become a microchip, right? So all of you have microchips emitting the light in all of your in your house now, right? And think about what that means. It means this is what's really amazing about what's interesting about the way microchips are made is it's the style of manufacturing. What does that get to you? Why would you use this type of manufacturing? Why wouldn't you just use a lathe or a 3D printer, right? What this industry gives you is atomic level control, okay, and I'm not exaggerating, on billions of devices. All of you have to be able to have your LEDs in your smartphones, and yet cheap enough for everyone to buy. And I literally mean atomic level control, okay? Like then in every single LED, there is a particular layer called the quantum well, which the thickness of it traps the electrons and converts them to photons. And literally the thickness of that layer is on the order of 2 nanometers, 3 nanometers, something like that. Okay, that's 20 atoms, 30 atoms thick. And if it comes out 10 atoms too thick, the color comes out wrong and nobody's going to buy your LED. So they really, really do have to have atomic level control on billions of devices cheap enough that you can afford it. That's what's incredible about this type of manufacturing, right? Is that, and I really do believe it is the most advanced type of manufacturing in the world because this is so easy, because it becomes normal. There are machines in our clean room where we literally type in 20 angstroms, start, wait 5 minutes, take it out. And only this last year have I stopped to look back on it and realize, wait, I literally just typed in 20 atoms and hit start. Right? That's what, and then it did it for me. Like it was easy, right? So there's a bunch of different techniques to do that, but the bottom line is it's doable and repeatable, and you can do it on thousands of chips at the same time. So one of the methods that I think is different than, for example, a CNC mill, which is basically a motorized drill, right? Or a 3D printer, which I think of as a motorized glue gun, basically, is that those tools have to touch every part of your material. It's a serial process, right? So I know when 3D printing became big, I was really excited to buy $1 pots online. They're totally not $1 because it takes 4 hours to print them, and then it's actually not as cheap as you would think. The material might cost $1, but 4 hours of this tool time actually is really expensive, right? Because it has to touch every single pixel. What this manufacturing excels at is that every single step should make 1,000 devices. So if I'm going to add metal, it should add metal to 1,000 devices. If I'm going to pattern, it should pattern 1,000 devices. That's how you take the cost of all the facilities and the materials and all that stuff and make it really cheap. You divide it by how many devices you actually made. Okay, so that's an interesting, I think, just manufacturing mindset. If at any point I have to poke every single device by hand, I'm not even going to go that way. That is not a scalable process. That's not how I build thousands really cheap. Okay, so that's I put that out there for you, Hackerspace guys, just as a way to think about manufacturing. What makes it cheap versus expensive? It's actually our labor. Like my time is the expensive part, right? Like if you're sitting there in front of a 3D printer or whatnot, I mean, that's the expensive part, right? So the more devices you can make at a time, that's why plastics are cheap. Plastics are incredibly complicated, right? They have to purify all these chemicals. Like, doesn't that must cost a huge amount to purify these chemicals, but then they just pour it into a mold and make 10,000 devices at the same time. That's how you get them really cheap. So let me talk a little bit about that. A laser pointer, like I pointed out, same kind of thing. If you actually pop open a laser pointer, you can see I love popping open things at home. You guys have, my family has to put up with me breaking everything at home. If you look at the actual laser is actually this little grain of sand at the end. Again, 0.5 millimeter wide. all the rest of this is really just to make it big enough for your hand to be able to hold it and big enough for a battery to fit in there. The laser is actually still a 0.5 millimeter wide. And one of the keys is you definitely do not make one of these at a time. That would be really hard to hold and really hard to do anything with. So really, you want to be able to make 1,000 at a time. That's how you make red lasers 50 cents each. I will point out the other stuff going on in this package is really interesting. Cardboard coated in some kind of conductive paint, conductive epoxies. I mean, it's really, and if you look closely, there is one thin wire that connects the top of that grain of sand to the contact, but all the rest is cardboard and glue. Pretty awesome. That's how you get it down to 50 cents. If you think about the word chip, microchip, you probably picture this little box with legs. Hopefully you're not thinking Doritos. You could be thinking Doritos too. It depends what time of day it is. This is, for example, is a USB memory stick. I got a couple of these popped open at home, right? That's not actually the chip. That's actually the package to make it so that you can actually handle it. If you, in this case, melt off the plastic on the top with an acid, the actual chip is this piece of crystal inside. I think that's why it's maybe called a chip, because all of these semiconductors are actually crystals, and crystals always break in a preferential direction. Just like a quartz crystal will always have exactly that hexagonal shape. Silicon crystals will typically break in squares or cubes. So here you can see actually this acid has destroyed the heck out of this chip over there. All the stuff's destroyed on the top. The only thing that survived are these little gold wires that go to each of the legs. Okay, so this makes it, if I had stuck my finger on top of this live chip, my finger oil would destroy it, these wires would all get bent, like I would destroy that chip. So really what the plastic packaging does is make it so you can actually hold it without damaging it and do something with it, right? So the way you make a microchip, when you're making things that are very small, we really care about dust. And so we do all of that in a clean room. I think a better way to think about the word clean room, if you read articles, they call them a fab, they call them a clean room. Clean means low dust, right? I think it's actually easier to think about it like a machine shop, right? So it's like a standard machine shop. That kind of gives you a frame of reference. That means you're going to be wearing safety glasses. You're going to have closed-toed shoes. You might have some other safety protocols, right? But it's the kind of machine shop where you can make things smaller than a drill bit can make. Like Mike, what would you guess is like the smallest size of something, a drill bit you could get, like for a hand drill or a CNC? Like, any guess? Yeah, like what would the smallest be?
CNC? I don't know.
Like kind of approximately, like what do you think? Eighth of an inch, yeah. And if you get smaller than that, it's going to keep breaking. Exactly, right? So even that, two problems with a drill bit. One, it has to touch every single spot. You can't make 1,000 at a time, right? And two, it's going to keep breaking, right? So this is the machine shop where you can make things smaller than a drill bit can drill, okay? That's the way to think about it. And you're going to do it at scale, meaning we want to be able to make 1,000 at a time with every single step, okay? So that's kind of the different mindset in this clean room, in this machine shop. And then, of course, to reduce the dust, the biggest producer of dust is actually the human beings, right? It's my clothes, it's my skin flakes and hair and all that stuff. So really, the plastic suit is actually to protect the environment from you and keep all the dust inside. And then in addition, this is not our clean room, but an example of a clean room. You have HEPA filters on the ceiling that are forcing clean filtered air down. And in this case, they have a subfloor, meaning that the clean air goes down through the floor. In our lab, it actually recirculates back up. Okay, so this was actually invented in Los Alamos, the idea of a clean room, when they were dealing with thulium dust. They came up with this whole idea and the HEPA filter to try and deal with that. Now it's, although it might look like a really weird environment, like I said, we actually have a number of clean rooms here in Santa Barbara, right? So like literally as you're driving on the highway, if you see those big liquid nitrogen tanks, each one of those is a clean room. We have a number of these in town, and it is a bit like a mad scientist laboratory, but really anyone can get in there and learn to use it like any other machine shop. You could learn to machine, you can learn to do carpentry, you can also learn to make microchips. Any questions so far? Again, don't. It's the cheapest way to get really pure air, right? So most air is 85. The question was, what does the clean room need liquid nitrogen for? It's one of the cheapest purified gases you can get because 85% of the air is nitrogen. It's actually a byproduct of fertilizer production, if I remember correctly. So if you boil that off, you get really pure nitrogen, which we use it for air guns basically, but we also use it for processed gases where we need to introduce nitrogen with 99.9999% purity. So
We're not necessarily using it for
we also use it for that sometimes. Rarely, less commonly, but sometimes. Depends on the machine. We do have some machines where you have to pour liquid nitrogen in them to get them to work properly. Yep. So a number of different uses. And of course, for making ice cream. Liquid nitrogen ice cream is great. So just like woodworking, I think woodworking is actually a great analogy to making microchips, because it's the same kind of thought process, same kind of person, same kind of mechanical thinking. So just like woodworking, you don't have to learn to grow the tree to be able to start doing woodworking. You just go to the shop and you buy the right type of wood, right? You buy, what is it, hardwoods for outdoor furniture. You buy pine if you want to do something cheap. So similar here, there's a whole different expertise of people that just grow the crystals, okay? Silicon is one type of crystal. It's the cheapest crystal you can get. And let me also point out that I believe that silicon is effectively the highest purity material human beings have ever made. And it's basically because of this industry. So when you grow this into a single crystal, what that means is all the atoms are in perfect order, and then actually you can use that to push out all the impurities. So for example, if you go look it up, like the NIST standard for the 1.000 kilograms is a single crystal ball of silicon in Colorado, in Boulder, Colorado, also made of silicon. But because silicon comes directly from sand is silicon dioxide, same thing that it means glass, right? If you heat it up and get rid of the oxygen, you're left with silicon, and then they do a couple of other cool metallurgy processes to make it ultra pure silicon. You're left with, it means that it's really, really cheap. You don't have to go to some exotic place to mine it. You can literally get it from beach sand, right? So the purest material that human beings have ever made, silicon, I can buy these wafers for $10 a pop. $10, they're really cheap. So again, I think this is an example of how advanced the manufacturing is, that you can get some of the most advanced materials ever that cheap because the entire ecosystem works that well, if that makes sense. This is an example of the original silicon. They grow it out of a molten pile of molten silicon. This is single crystal silicon. And then they slice that into individual discs. These are what we call wafers. Maybe another food analogy, I guess. And what we mostly work on are these flat discs, these wafers. Okay, silicon is one type of crystal. You actually picked it. So most of your electronics, anything that runs on electricity, phone or fire alarms, will all have silicon electronics in it for doing computations and whatnot in it. But other types of crystals will be used for different types of chips. So like LEDs, like our gallium nitride, some infrared lasers or indium phosphide. So you pick different crystals depending on what you're trying to make. It doesn't really, you saw all the different examples of what you can make. The bottom line is that if you learn to actually make microchips, if you learn to make one type of microchip, you now know the steps for making any type of microchip. So there's really only 3 main steps that you do for making a microchip. I'll go through these in a second, but again, the analogy to woodworking, I think, is really valuable. If you worked in a wood shop and you learned to make a cabinet, and then a week later someone said, hey, we're gonna go frame a house, and you've never framed a house, you could actually figure it out, right? It's not that bad. It's still wood, it's a different type of wood, still, you know that there's 6 different types of saws, and there's a certain type of saw for this, and a different saw will use that, right? You can figure it out. So similar here, right? If you learn to make one type of microchip, you can pretty much figure out how to make any other type of microchip. Just like machining or woodworking. So the 3 big steps are, before I go into the 3 big steps, any other questions? It's all good questions so far. There's really only 3 steps. This is an oversimplification, but this is how I like to think of it. There's basically 3 main steps for making any type of microchip. Lithography, patterning, etching, removing material, and deposition, which is adding material. Okay. I will point out that many of these terms, substrate, meaning the initial crystal that you're starting with, lithography and etching are actually art terms. So artists have actually had to figure out this problem a long time ago. The problem of how do I get the expensive artist to draw something once, but then I reproduce it 1,000 times really cheap so everyone can afford a book. right? That's what the printing press did, right? It used to be monks individually scribing, and it was too expensive, and no one could afford books, right? So artists, a lot of these terms come directly from art, and a lot of the techniques come from art because that's the same mindset. How do I reproduce something with a print many times really cheap? Did you have a question?
Oh no, just photolithography and 3D printing. That was like the original. No, resident and they call that photolithography.
Okay, it's actually very similar actually. So if you break apart the term, the question was that in light-based 3D printing, they also call that photolithography, and it's exactly the same reason, because if you break this apart, you're using light to draw into stone, or in our case, crystals. It really just means patterning or printing using light, is what that means. Printing, again, meaning I'm not touching every single pixel. I'm going to do the entire thing in one go, right? One big print. So the way that we actually do this in the clean room, in the fab, is you take it, if this is a cross-section of your starting material, so some crystal. I will point out that, again, you buy this crystal, but they've actually already grown crystal layers on it that correspond to whatever device you're trying to make. So I mentioned those quantum wells that determine the color of light output. Those will already be grown on the wafer, but otherwise the wafer will be blank. It'll be totally patterned. You will see no patterns on it. Those layers have been grown uniformly across the entire wafer. Okay, so we have no, and we are trying to get to a final 3D structure in the end, right? So right now it's just kind of one-dimensional. We've only grown layers on it. The way you do this is you start up here. You will coat the wafer on a spinner with a material that actually is very, very similar to nail polish. So think of nail polish, starts off liquid, right? And it's kind of goopy. So we'll do the same thing here. They can literally take a pipette or a syringe and just like literally pour this goopy brown liquid onto your wafer. And it's still liquid, it has those solvents in it. And then instead of waving your hands around to dry it up, instead we put the wafer on a, then you spin it. And spinning the wafer at, for example, 2,000 RPM, 3,000 RPM with a vacuum holding it down, that will actually cause the goopy layer to spread into a very uniform thickness. So you have a nice controlled uniform layer of this nail polish-like material on your wafer surface. And then instead of waving your wafer around, put it on a hot plate to bake out the solvents, and now you've got a hard material, like hardened nail polish. That analogy, by the way, is not just a silly analogy. It really is like nail polish. If that tells you anything about nail polish, it tells you that nail polish is way more advanced than you probably realize. So now that you've got this hard material on the surface, and the reason it's like nail polish, they also dissolve in acetone. Anybody know what the main component in nail polish remover is? Acetone. I mean, really like the same chemicals. Okay. So now you've got this hard material, this hard coating of photoresist on your substrate. It's light sensitive, so actually it's really more like UV cured nail polish, where now ultraviolet light can actually change its properties. Okay. Then use ultraviolet light to, for example, shoot through an already patterned plate that has your pattern already on it. So it blocks light in some areas and transmits light in your glass plate in other areas. Right, so that's what this would look like. So this might be metal blocking the light on my initial stencil, and this might be glass where the light actually gets to hit my wafer. And that changes that allows the exposed areas in one type of photoresist to then be developed out. So you literally take the wafer, dunk it into developer. You can see this comes straight from analog photography. And where in this type of resist, wherever the light hit it, the developer literally washes it away. So you dunk the wafer with this brown coating on it into developer, and as you're watching, you will see the pattern start to come out, and you'll see like brown stuff floating off into the beaker. Okay, so you can again you're doing this all by hand, and you can literally do this by hand. I'm convinced that you can do this in your kitchen. I'm still working on it. Okay, so now I have the term resist also comes from art. Anybody here ever heard the term resist in art? Yeah? Where have you heard it? Exactly. In silk screening for patterning T-shirts, right? Again, another case where you want the artist to draw once and then you want to print 100 T-shirts, right? And you've also heard the term resist? Same place? So what resist means in art is something that protects your substrate. In one case, it might be the T-shirt. In our case, it's the substrate is the silicon or crystal wafer, right? So now I've got this hardened plasticky like material that's actually protecting my substrate in some areas and expose my substrate in other areas. So now I can do something to it and get my 2D pattern to go into my substrate if I add one of the other two steps. So let's look at the other two steps. Before I go to the other two steps, any questions on this? Okay. I will say there are, just like having 7 or 8 different types of saws for woodworking, we have 7 or 8 different types of patterning tools at the NanoFab. Some are very fast, but can only do larger features. Large, by the way, in the NanoFab means like, 200 micrometers or 50 micrometers. A human hair is about 100 micrometer, and we call that big, which means it's super easy to do 50 micrometers. I don't even think about it. We just do it, and it basically works. And then you have other tools that are very, very slow, but can do 2 nanometer level patterning, right? So that means this resist area might literally be 20 molecules wide, and you can do that kind of level of patterning, right? So you pick the right type depending on what you're trying to do. Yes, you have a question?
With the smaller patterning, how do you actually get features that small that are smaller than the wavelength of the light?
That's a great question. The question is, how do you get features smaller than the wavelength of light you're using? So we're using ultraviolet light on many of these tools. So that's like 200 nanometer type of wavelength, and you can typically only make these kind of ridges are on the order of 200 nanometers, maybe a little bit smaller than that. So you can't use light. Light gets, well, the other way we do it is we have tools called electron beam lithography. So they use electrons. So the faster you make those electrons, the smaller their wavelength. And so if you use electrons instead, that, by the way, that's the same technology that was in the old cathode ray tube TVs, right? They're shooting an cathode ray means electron beam, right? So same technology, use that instead, and now you can get to much smaller feature sizes, much smaller. Then it's the wavelength of the electron is what your limiting factor is. And you can accelerate those faster to try and get smaller wavelengths. Yeah, good question. There's also other ones I can tell you more about, focused ion beams. The most advanced tools that ASML makes are extreme ultraviolet. So instead of 200 nanometer wavelength, they're a 13 nanometer wavelength, which is actually just about borderline X-ray. So that's a whole other 30-year story of how they even do that. Those tools are some of the most advanced, complicated tools ever. They're really amazing to work on from an engineering standpoint, mechanical engineering standpoint, fast robotics, extremely precise down to nanometer level positioning. I mean, really, really sophisticated. Yeah, good question. This is an example of one wafer I made for Professor Phil Lubin's group here at UCSB. This was for, they were trying to make a sail for photonic propulsion for shooting a spacecraft at relativistic speeds. But really the key here is that this is a silicon wafer I'm holding, right? And that brown material on the outside, that is the photoresist. And you can see I've exposed the pattern of this hexagon. The idea is they wanted to be able to remove all the silicon in the middle between the hexagon and protect it in the hexagonal structure just to give it mechanical stability. Turns out it still didn't have much mechanical stability, and I kept breaking these wafers actually, so didn't quite work out. That's research for you. Okay, so still at some point you do have to draw your thing on a computer. You have to draw your design on a computer. So where does the pattern even come from? You design it on a computer. Now, some of you guys probably know CAD drawing. You're probably thinking about 3D printing and stuff like this. These are way simpler. You'll notice that this CAD is just 2-dimensional. It's really, really simple, right? Like if you guys are doing SolidWorks and AutoCAD, it's actually more sophisticated than this. We're doing 2-dimensional structures, but we are picturing a 3-dimensional device, right? So I'm picturing the process steps where this is going to be protected and this area is going to be etched, for example, for the Mesa etch. Right? And I'm going to add metal on just the yellow areas, for example. So I am picturing a 3D structure in my head, but the actual pattern I'm going to use for my stencil is actually 2-dimensional. Right? So the CAD drawing is pretty easy. It's simulating the device and making sure the device is actually going to work. That's the hard part. Right? The drawing is actually pretty easy. Okay, and then you do have to, at some point, print that serial method that touches every pixel. So, for example, in this case, I would take maybe just the bond pad metal pattern, only the yellow part, and I'd print that onto a glass plate. And that will be printed with a tool that actually you can literally print it with a laser printer onto transparencies if you want to. So you can use just black and white laser printer on a plastic sheet to do this if you want to go kind of really low tech. That printer is going to sit there and touch every pixel, right? And if you're trying to write 1 micrometer pixels, that can take 4 hours to write a whole plate, but you only do it once, right? So you do that once, and then from that point on, you use the glass plate to shoot the entire wafer in 20 seconds. So 4 hours to make the plate, but then every wafer after that's 20 seconds, right? So I can still have a path to scale even if I did the serial process once. After that, I always go to the parallel process after that. Does that make sense? Okay, so that's how the patterning works. So I've protected one area of my substrate, exposed other areas of my substrate. Another step I can do is removing material, called etching. Again, comes right from art. So let's say I had the resist protecting some areas. I could, for example, etch, and that, if you notice, look carefully, the resist actually does get thinner. I did etch my resist, but there's enough of my resist that it didn't go away. It still protected the substrate, and I can now transfer that 2D pattern. Now it's become 3D. Right now it's transferred into the metal and glass of my actual microchip. Okay, and really this photoresist is actually just a temporary material. I want to be able to remove that afterwards because my final device shouldn't be able to wash away an acetone. It should be metal and glass. It should be fully solid. Okay. There are 2 different types of etches. There's lots of details here. I will tell you right now that dry etching is one of the most complicated physics that we have ever dealt with, and it is really fun to play with. Let's say you started with this, the easiest thing to do is a wet etch. Literally just dunk your wafer into an acid that is chosen to eat away whatever the substrate material is or whatever you're trying to remove, right? It's cheap. You can buy hydrochloric acid. You can literally get it on Amazon delivered to your house. I don't recommend it. You can use oven cleaners. Like, you can use household chemicals to do this, actually. But, now you have to wear PPE. You have to have good ventilation. So it's a little bit more dangerous, a little bit more nasty. You got to be careful with it. But it's easy, right? All you need is a fume hood and some chemical, and you dunk it in there, right? Some of them are really nasty. Hydrofluoric acid, you got to be really careful with. Or you can do a dry etch where you actually use a plasma etcher to do this for you instead. And that gives you more control. If you do a wet etch, the chemical will go in all directions. You can't really it's not quite as controllable. It'll work, so it's not super controllable. If you want a really controllable process, you use a dry etch using a plasma. Anybody here ever seen a plasma? Raise your hand if you've seen a plasma. Okay, where have you seen a plasma? Yep, every single fluorescent bulb is a plasma. A lot of people don't know that. We also recently figured out how to make plasmas in our microwave, which is really fun. I'm hoping to make microchips in the microwave at home. Hit me up if you want to see how that's done. So it is. If you hear plasma, it might sound. For example, Jacob's chemistry book last year really annoyed me. The first page said plasma is the 4th state of matter that can be found in the higher upper atmosphere or on the surface of stars. And I was like, how about every fluorescent bulb, right? Like, I mean, it's probably in your house right now. So it's really normal, and it's really well known. It's 100 years old. So controlling a plasma and using that to do stuff is actually really not that complicated. I mean, it's complicated, but it's well known, if that makes sense, right? So the tools are pretty easy to use. I don't have to be a plasma physicist to be able to run the machine that does this. So let me explain real quick how that even works, just real quick. So for example, first thing you'll see is that you actually pull out all the air from the chamber. So this, for example, is a vacuum chamber. It's got rubber seals. Put it on a vacuum pump, pull all the air out, and then flow in only a pure gas that you want to use for this etching. So in this case, for example, argon gas, for example. And the top and bottom of the chamber are electrodes. This is the same as how a fluorescent bulb works, right? There's no filament going through the fluorescent bulb. There's just electrons on either side. And you apply high voltage to those to rip the electrons off the gas. That's how you get the light, okay? Those are also vacuum, right? Fluorescent bulbs are also under vacuum, which is why they're so much fun to smash. So you apply AC electricity between those 2 plates. It kind of rips off the electrons, some percentage of them. And when you do that, the electrons are actually much smaller and more mobile than the nuclei. They're much heavier. So the electrons actually will hit the electrodes. One of them is grounded, so this is effectively 0 volts. And the bottom one, in this case, for example, is left under DC isolation, meaning when the electron hits it, it can actually build up a voltage. So you'll end up with an actual voltage between your plasma, which is now conductive, right? The gas is now a conductor, and the bottom plate. And you can see positive, negative. If I put my sample on that bottom plate, that voltage difference attracts the gas towards my sample and batters the sample. And it's like sandblasting with atoms. As literally, when I turn these things on and I see the light glow, this is what I'm picturing in my head, is AC electricity repeatedly battering my sample with atoms, okay? That's how you do atomic level control and very small features, is you use atoms instead of particles of sand, okay? That's basically how a plasma works. If you could do me a favor and hit play on that video, that would be great. This is a video, thank you. We don't need sound either. So this is a really simple tool for using atoms to blast metal off of a target, and that will coat my sample. But basically what you see me doing here is I've pulled vacuum on the chamber, so now I can't open it anymore. And I put my sample inside there on that little plate. That's the bottom metal plate. Fast forwarding, you can see the vacuum gauge pulling, reading what the vacuum level is. Once I've got low enough vacuum, then I'm going to turn on the gas. So here I've got gas flowing in. And then I've turned on the voltage, and now you can see the plasma there. So it really does look like a fluorescent bulb. It is the same technology. And that plasma is actually, in this case, repeatedly battering up and down on that metal ring, and it's shooting that metal all over the chamber, which is why you can see the chamber is kind of like darkish gray on the top there. That's literally the metal being sputtered. They call it sputtering onto my sample. Okay, so really easy to use. This it is very advanced technology, but as you saw, like that's a fully manual tool, not computer controlled. I'm just hitting buttons and turning knobs. Okay. There are more advanced tools. So here's a computer-controlled etcher. That last tool, I don't know, you can probably buy those for, I don't know, a couple $1,000 or $1,000. This tool is $1 million tool. And the actual etching chamber is down here. So this is where the actual plasma etching happens. And all the rest of this is the support to keep that thing running really repeatably, reliably, that every etch is the same. It has potentially some dangerous gases in there, and gas delivery, liquid cooling. As you can see, my friend Nick here, computer controlled. It's got robots to pick up the wafers and put them in there for you, right? So you can go as sophisticated as you want, right? I hope when I pointed out, you know, vacuum, fluid delivery, liquid cooling, hydraulics, pneumatics, computer control, it's all the same stuff that you find in a car. Right? So cars actually are exactly as sophisticated as these tools. The only difference is that they make 30,000 cars a year, and that's why they're $20,000. If they only made 200 a year, a car would be $1 million tool exactly as complicated as this. I point that out because people who love repairing their cars and tinkering with mechanical things are some of the best equipment engineers that we have. That and military vets have like learned all this cool. They've typically done lots of trainings. They know how to deal with hazmat and chemicals and procedures, mechanical thinking. Good example, Mike. This guy asked me some of the hardest questions I ever get. So I mentioned that to lower the bar. If you're thinking, whoa, I probably couldn't make microchips. Actually, you probably could if you're one of those kind of people, right? If you like upgrading your own car, you're maybe the same kind of person who actually can learn and be really great at troubleshooting these things. I will point out a sad story. This particular tool, actually dead right now, giant $1 million paperweight in our clean room, because the computer will only blue screen as soon as you pull it up. So some communication error, yeah, very complicated. Right? Those things are very hard to. What was that? No. I wish if we knew what it was, it would be fixed. Been down for a month. Luckily, we have a backup, so we have a second tool that's exactly the same that's still working. Okay, so that's etching. Okay, I'll go through this a little bit quicker, but with deposition, that's adding material. Oh, one thing I'll point out, right? You put your entire wafer in here, and it etches the entire surface of the wafer at the same time. So again, that's that parallel processing. Yes. Good question.
Maybe I'm jumping ahead a bit, but sorry, 2 seconds. Wafer sizes. So when you're doing prototype for small, like single wafer run, are you using 4-inch wafers or larger ones, or does it depend on the size?
Gotcha. The question was, are you using small pieces or large full wafers for prototyping? It really depends on the cost, right? So silicon's the cheapest thing I can get. So if I can figure out how to do it on silicon and still answer the same question, definitely do it on silicon. So you'll find a ton of biology, biomed, or quantum computing type chips where they don't actually care about the crystal that they use. We'll just use silicon because it's ultra cheap, right? But if I am making some new type of infrared laser, the crystal growth on that can be incredibly expensive. Like you can buy one wafer this big for $25,000, right? And so you probably don't want to use that entire wafer in one experiment. So depending on what your costs are, yeah, people will absolutely cut those into small pieces and then do 30 experiments. So it really depends. Some of the companies that have more money, they don't want to waste time developing a process that only works on 1 centimeter. They know we have to be able to make 10,000 at a time. So we're going to develop the whole process on the expensive wafers, so that we're always doing it at scale, right? So really, the way you do it is different, right? You need different hardware to handle a small piece than a big wafer. They don't operate the same in the tools, so it kind of depends. It really depends what you're trying to make and how much money you have, really.
My second question was, it looks like you're doing multiple patterning operations on the same wafer. How do you align the patterns when you do the second operation and the third operation?
Yeah, it's a great question. The question was, if you're doing multiple patterning operations, how do you align? The simplest methods are literally just little screw knobs that will physically move your wafer with respect to the patterned mask plate, the stencil, right? And you literally look through a microscope and you line them up and you align a rotation. So you can just do it purely mechanically. That's effectively what magazines and T-shirts do. If they have multiple colors, they have the same kind of thing, right? They'll have little alignment crosshairs somewhere where you can't see them, and they'll line up the multiple layers. So that's the simplest way. But the most advanced those are the lithography tools that do that, right? It's the patterning tools that have to line up to a previous pattern. So the most advanced ones have laser interferometric stages that have 4 nanometer placement accuracy, keep it all temperature controlled and humidity controlled so that the expansion of the tool because of a 1 degree change doesn't ruin your alignments. There's a lot of things you have to be in a low vibration area, low electromagnetic interference. So if you're trying to make it, nanometer level precision, you need to take all these other precautions. But at the simplest level, you literally just put it on screwdrives or micrometers that kind of just move your substrate with respect to the original pattern, and then only shoot it once it's lined up. That makes sense. That's the cheap way. I'm always interested in the cheapest MacGyver way to do something in addition to the most expensive advanced way, right? Because if you can do it in the cheap MacGyver way and your device works, you've got a much better production process. So with a deposition, here's an example of using that pattern to actually choose where metal goes, for example. Okay, so let's say I had my previous cross section here, still has the photoresist protecting some areas of the substrate. If I add material on the entire wafer, I'll show you what that looks like. With a couple of different methods. That plasma I showed you actually was a sputter method where it's depositing metal everywhere. Evaporation is where you actually melt the metal in vacuum and it shoots up through the vacuum and coats the entire chamber. That's exactly the same as the old style filament bulbs. Remember when they were burned out, what they looked like? What did a dead bulb look like, remember? It would be dark and black, and the filament had popped. And the reason is because you're literally evaporating the filaments. And the bulb is a little vacuum chamber, and that filament is getting hot, and the metal is shooting off and coating the inside of the glass. That's why your bulb would turn dark gray, and the film is getting thinner and thinner and thinner until it pops. That's actually the same technique. We're just doing it in a large machine, basically. So let's say I coated my wafer everywhere in metal, and I still have my resist here that dissolves in, remember what it dissolves in? Acetone, right? Nail polish remover. If I dissolve that, it will lift off the metal that's on top of the resist, and you'll literally see little flakes of metal floating around in your acetone beaker. But then you'll end up with, and it looks kind of messy, but then once you clean it all off, we use rubbing alcohol a lot, isopropyl alcohol, clean it all off, and you'll see these beautiful metal patterns that on your wafer of wherever there was no resist protecting the substrate. That's a lift-off process. There's other ways as well. So for example, this is an example of what the machine looks like. Think of it like a gigantic light bulb. This is my friend Pratik. This is all motorized, right? So this bell jar comes up. This is a vacuum chamber. And that's for loading it. And then when you're actually going to run the tool, this bell jar goes down and it pulls vacuum, seals in the bottom, and pulls all the air out, right? So at the bottom here, in this little area here, we have, in this case, literally a little pot of gold pellets, ultra high purity gold pellets. And once you pull, and then your sample goes up on the top, your wafer goes up on the top facing down. So it's facing towards the gold, where the gold's going to come out. Okay? Put down the bell jar, hit start, it pumps all the air out. You have to wait 30 minutes for enough air to get out. And then you heat up, in this case, the gold crucible. You can either heat it with just a resistive heater. In this case, we actually use electron beams to heat it. Again, just like a cathode ray tube TV. Heats that up, and that gold will melt and effectively evaporate. It'll boil, so that's why they're called evaporators. And you get this, just like steam coming out of your kettle, you get gold molecules flying through the vacuum And as soon as they hit a cold surface, such as your wafer or the rest of the chamber, they instantly turn back into solid. On the chemistry phase chart, that's called deposition, where you go directly from gas to solid. So this is deposition by evaporation. And you can see actually even over here, the previous user, you see those little yellow circles there, the previous user had evaporated through the screw holes on the holder. So it literally coats the whole chamber. You get all your shielding ends up with titanium and tungsten and gold and platinum and all these different thin layers of metals on them. Question? I heard something. No. Oh, good. Yes. Wow. It is very interesting. I agree. So how do you get into fabrication? I really do think that the kind of people that have the imagination for figuring out invisible effects, right? So again, that actually does include people like carpenters, machinists. Not everybody even, and you're not going to run away screaming because there are chemicals. My wife would not enjoy this working in there. You don't mind wearing PPE and safety stuff, right? But I actually think this is like working in a mad scientist laboratory. It is so cool working in there. Even what that means that even when you have a day where like you dropped 8 wafers and you broke all of them and you're like, oh my goodness, I got to go back to the start. Still, I come out of there going, this is so cool that I get to do this, right? You still have bad days. But if you enjoy that kind of mechanical thinking, I literally heard one of my friends told me that Intel used to ask, tell me about your car, when they were trying to decide whether to hire technicians and equipment engineers, because that tells you a lot about a person if they have worked on their car, right? Like they spent 2 hours getting a stuck bolt out or re-drilling it, or they're persistent enough to get this thing working no matter what it takes, right? But again, it's all the same kind of systems: fluid delivery, computer control, mass flow controllers, all the same sort of things in the car. Also, from having talked to all the local companies, I think this is kind of what the workforce looks like for this industry. This is sort of the terminology they use, right? So I've been talking here about, and this is, by the way, apart from all the other important support staff like human resources, business development, management, all that stuff's actually really important. Keep the money coming in and make sure you're making stuff that customers actually want, right? I talked mostly about this microchip manufacturing, right? So some of the terms they use here are wafer technicians or manufacturing engineers or microchip designers, right? So a whole different office of people that just designs the chips. But I've heard that a lot of these companies actually they need more equipment maintenance engineers than they do wafer fab, because they have 200 pieces of equipment. And they're all different and they all have their quirks. And when one breaks, like you need someone with that kind of troubleshooting to figure this thing out. I mean, you guys have tools here as well, right? A certain kind of person can take that apart and actually get it working. Then there's people like me where I'm like, why do I have 5 screws left over? And I don't know why it's making a clunking noise. Good enough. You don't want me doing the equipment maintenance. My wife can relate to that one. In addition, the facility itself is incredibly sophisticated, right? So airflow, cooling water delivery, all the water has to be purified so it doesn't have ions in it that are going to mess up the electrical properties of your chip. Gas delivery and gas boxes and welding. I mean, like our facilities guys are very sophisticated. That's for example, when we talk about plumbing and welding, we're not talking about like unclogging toilets. This is the most advanced plumbing in the world, right? Double coaxial welding for dangerous gases that have sensors on the outside and sensors throughout the whole lab. Like really, really sophisticated facilities too. And then lastly, if you've made, like I said, 1,000 chips per wafer and you made 25 wafers, then you cut them up into individual chips. What do you do with those? You need even more manpower to turn those into an actual device, right? So the system assembly and testing is a whole other thing, right? So you take 1,000 chips and now you need to test them and make sure they work. You never want to waste manpower on a chip that doesn't work, and add wires to them, put them into your laser pointer or whatever your chip is, right? Even more manpower on this side, potentially the largest manpower need, because at some level it's serial processing. You have to do one chip at a time, right? So more of the lab, you might literally need 10 identical pieces of every equipment just to multiply by 10 how many we can put through, right? So a significant portion of your lab is all of this stuff as well. And then sort of the job levels and education levels in this industry are, they call them operators, which means somebody like fully entry level. You may not even really know how the microchip works, but you've learned the operating procedures. you're working at one machine or just doing wet etching, and people come to you and you do the wet etch and you follow the instructions. Above from that is technicians. Oh, by the way, I should say you can jump in anywhere here and move your way up. Lots of stories of people doing that, right? So you can either go to school and get more education to get this, or you can get in the industry and learn it on the job. And there's tons of stuff you learn on the job that you won't learn in school too, right? So really, industry experience gets you a lot in this industry, right? Any manufacturing industry probably. Technicians are more like, oftentimes are not just working on one machine. They might know how to use all the machines. They might take the wafer and actually run it through the whole fab process. And then the engineers might be the highest level. And again, you can work your way up to that where you actually understand how the device works, or you really are able to troubleshoot complicated problems. You have 20 years of experience. So if a technician comes to you and says, hey, is that what this wafer is supposed to look like? You know the answer, or you know how to figure it out, right? So those are kind of at a high level, sort of the education levels. But again, although I put the education levels here, the job levels, although I put the education levels here, there are lots of stories of just going through that in the industry, right? You don't have to, school is not the only way to get it. But I actually absolutely think that school is one of the fastest ways to get it.
Yeah.
Yes.
Pretty much the question I was going to ask you is, how could you learn about this besides in school or in the industry if you wanted to make it?
Yeah, it's a good question. The question was, how do you learn about this besides school or industry? You have to get in there or do it at some point, right? Like that's almost like saying, like, can I learn carpentry without doing carpentry, without getting hands-on, right? So you still have to do it at some point.
Yeah, but you can read up about carpentry, or do you read up about this process?
Yeah, actually, the question is, you can read up about carpentry. Yes, you can read up about these, right? So there's a bunch of videos on YouTube of people explaining this. One thing that you want to be careful about is that in carpentry or car repair, most of them are made for like the regular layman level. But if you go read about semiconductors, it is so advanced that half the videos are about the most advanced chips in the world, and they're talking about the whole thing, which is totally mind-boggling. And even in that company, there's no one person that knows how to do the whole thing, right? So be careful, because it is super advanced, but looking at the entire thing is like saying, well, here's a city. Isn't that amazing? Here's how the city works. But nobody actually is able to design everything about the city, right? So if you're actually going to get in, what you want to do is find those that are really talking about how does this one process step work, right? And how do they go together? So actually, if you email me, I'm happy to. I actually put together a series of videos by a colleague of mine, Professor Matt Plyle at UNM, where he literally goes through each of these steps. Lithography. Let's talk really about lithography and different types and how does it work. Here's etching. 2 separate videos just on etching and all the things you have to think about. So I actually have a kind of a Google Doc that lists all of those. I'm happy to send that to you. That's kind of a good way to learn about it and learn more about it. Still, just like with carpentry, you do have to get in there and actually try it. And then you'll find out, that video said this was supposed to happen. That's not what happened, right? So how do I figure this out? So you still have to get in there and actually learn how to solve the problems. I'll stop there and take any questions. Yeah, go ahead.
You didn't mention doping. Is that not done anymore?
Oh, there's a lot of steps I didn't mention. Electroplating. We did electroplating. Remember we did electroplating in our house, Jacob, with like hydrogen peroxide and things? That's another way to add metal to all the surfaces. Yes, doping is one way to change the crystal. The reason I didn't mention doping is because I'm not talking about a particular type of microchip, right? I'm talking about here are the steps for making any type of microchip. And if you go into the process for a specific microchip, you're absolutely going to learn lots of things specific to that type of microchip. Does that make sense? So doping is a way of changing the electrical properties of silicon, for example, and other crystals as well. Those are all kind of the process steps you will learn, right? So similar to crystal growth, I didn't talk at all about crystal growth. That's a whole other expertise, right? So
You guys don't deal with silicon exclusively, then you deal with
that's right.
novel kind of.
Yeah, actually our expertise is in if you look at the periodic table, silicon is in group 4, carbon and silicon. And we deal with also a lot of 3, 5, so the elements on either side of those that also combine into the same crystal structure because they're only one element away. So that's indium phosphide, gallium antimonide, gallium arsenide, a whole bunch of other crystals, and each of those has as good for a particular use. Certain different colors of light or extremely fast transistors. We do our undergraduate classes at UCSB. They do NMOS transistor circuits, so they do doping. And they do all the kind of standard silicon, more of the standard silicon processes. Yeah, go ahead.
What was that chip that had been meant to have a kind of a honeycomb
Okay, the question was, what was that hexagonal wafer I showed? That was a full wafer. The idea was to leave a structural lattice so that the wafer itself is pretty strong, but then thin the silicon as much as possible because they're trying to make a spacecraft as light as possible. So the less material they can have, the better. Thin the silicon, but still make it strong enough to survive a rocket launch. And I think they needed something like 1,000 of these that you would shoot a laser at from Earth at this giant mirror made of ultralight mirror, and the ultra high power laser would basically convert its momentum into, it would transfer its momentum into the spacecraft and accelerate. So that the point, you should look it up. Phil Lubin, Deep Space, his website, the really amazing stuff. Everything he tries to do is, you think, oh yeah, that should be possible. Then you look it up and you're like, yeah, you're instantly at the cutting edge of technology. Like nobody knows how to do that. It's really amazing research. But yeah, the idea is for photonic propulsion. So instead of carrying your fuel source with you to space, which means that if you have to make it bigger, you also need more fuel, and you kind of get this diminishing returns. Keep the fuel source on the ground and shoot that to the spacecraft, right? So you can have, all your nuclear power generators and coal power plants powering your spacecraft in space. That's the idea. It can only accelerate it. I don't think they know how to make it stop. It's just going to shoot past your planet of destination at light speed, but that would still be amazing. Yeah, good question. Any other questions?
A question here from the earwax.
Oh, okay.
What's the largest single chip that you've made, either by components or by chips?
The largest single chip I actually made was the giant red waveguide spiral I showed that I graduated on, where you had a single device that was this big. What's really annoying about that is it means one defect means the entire thing doesn't work. So when I finished my PhD, I had documented all the wafers I made, and I went through and tabulated them up. I made 97 wafers, about 50% of which didn't do anything useful. So yeah, when they're really big, it turns out it's really hard. Your yield is either 100% or 0 and nothing in between. So that was a 4-inch wafer to give the area.
And then, is there anything dangerous involved in the process? It sounds like you're using chemicals, and so like, what are the big dangers involved?
Yeah, absolutely. Let me address the chemical dangers. So we use acetone and other solvents. So for example, NMP, if I remember correctly, you can also find NMP in like paint thinners and epoxies and stuff like that. Acetone is found in every nail polish remover. Isopropanol is rubbing alcohol, right? Think about all the industries that use the same chemicals and really don't have that many safeties, right? So yeah, you're supposed to wear a respirator if you use paint thinner, but does everyone wear a respirator? Nail salons, sadly, if you're not following all those protocols, a lot of people get chronic coughs from breathing acetone all day long, right? In our lab and in this industry, they make enough money and it's valuable enough that we do everything inside fume hoods. So all of those chemicals are inside fume hoods and you never smell them, right? Same with, sometimes you might have to use acids. So absolutely, like you have to do those safely, but they're all in fume hoods. They're all laminar flow hoods, so the air never comes out. Same with environmental, actually. We follow all the environmental protections. There's a maximum amount of fluorine you're allowed to drop down. We have all the infrastructure for scrubbing the water of fluorine, measuring the acidity, and there's so much infrastructure in the facilities to keep all that stuff safe. And then, like in any machine shop, again, I think thinking of it like a machine shop is really, really helpful, because in any machine shop, there are safety things. You got moving parts, sewing machine, not super safe, but you're going to learn to use it safely, follow the procedures, keep your eyes open, right? So a lot of those are set up in our lab by engineering controls, right? So here's the operating procedure. You get trained, you have a safety training, and you get trained on that tool, and we make sure that you know how to use it safely. So very similar to really any other machine shop, moving parts and mechanized parts, right? So I think the safeties that you do have in there are very similar to other industries, and you got to figure out how to do them safely.
And one more here. Does your fab keep busy enough to run multiple shifts throughout the day to maximize production?
The question was, does our fab keep busy enough to run multiple shifts to maximize production? Our lab, being an open use lab, means that we just keep the lab available for other people to use. So actually, I'm not hiring all the people using the lab. They're paying us an hourly rate to get in there and make whatever their company makes. So some of those companies have night shifts. Some of them are only day shift. We train users similar to a hackerspace kind of model where we train you on all the safety, we give you the quizzes, and we refresh your quizzes and all those things so that you can go in there unsupervised 24/7. So it's actually open 24/7. You just flash your smartphone to get in. We charge by the hour, just by when you log in and log out. You can use any equipment, right? So you can use the most advanced equipment or just a microscope, mostly the same hourly rate. So it's not up to us, but yes, there are people in the lab basically all the time. The busiest times are daytime, like 8 a.m. to 5 p.m. 10:30, super busy in there right before lunch. But yeah, even on the weekend, you go in there on the weekend at like 7 p.m. and you'll see 1 or 2 people in there. Graduate students often tend to be night owls and work way off shift. So I've done that myself. Yeah, good question. Any other questions? Okay. All right, I'll stop there. Happy to give you my business card. If you guys want to come by and actually do a tour of the NanoFab, I'm happy to do that. Again, I do that a lot. I'm really excited about this. I will talk your ear off for hours, so please stop me if your brain is melting. Yeah, happy to talk to you guys more about it. Sure. Are you able to fast forward there, fast rewind real quick there, all the way back to the?
I also got a question.
Yeah, I'll show you how to. Yeah, there you go. That way. Thank you. Yes. Yes, sir.
So on the slide where you show the photoresistant layer, the brown layer,
Mhm.
what happens to that photoresist layer? Like, does it just dissolve at some point?
Yeah. Good question. Yeah, Will's question is, he said, what happens to that photoresist layer? Like, if it's there on the wafer at some point. I did say it's a temporary material. So really, a full process step is do your patterning. So you've got photoresist in some areas, right? Do whatever the step is, etching or deposition, add material, remove material. You still got your photoresist on there. At the end of the step, you should be removing the photoresist. So removing the photoresist can actually be really complicated once you've taken this nail polish-like material and exposed it to plasma and ultraviolet and all this stuff. It can be really hard for it to come off. You actually want to strip the photoresist, remove it from the material, from the wafer at the end, and that's the end of your process step. So now all I've done is added or removed material and the photoresist isn't on the wafer anymore, right? And then now I can start my next process step. Add more photoresist, do maybe a different metal deposition, and then remove the photoresist at the end. So at the end of every full process step or layer, the photoresist should be gone. Does that answer your question? Yes, so it really is only a temporary material in that way. Yes, just kind of the stencil to define where you're patterning your wafer. Yep, great question. Yeah, you have another question?
Yeah, do you ever work with electromechanical devices?
Yeah, actually, the question was, do I work with electromechanical devices? The crazy engineering acronym is MEMS. At least it has a vowel in it, you can pronounce it, but what it stands for is quite a mouthful. Yes, those are basically microchips that have any moving part in them, right? So transistors don't have moving parts; they're just driving electricity, right? But the question was whether I work on any MEMS. Yeah, Pravium Research's devices, those have a moving mirror on them. And that is a MEMS device because it has a moving component. These devices are not MEMS. These are all solid state. So you put a fiber here, light goes in. These are tunable lasers. It modulates or turns on and off the light at 40 gigabits per second. Light comes out. No moving parts. It's all electricity and photons. Right? So no physical part of the chip is moving. This is the same chip packaged into a fiber package. So there's the fibers coming in and out. Okay, so also still no moving parts. But yeah, the most common devices that use MEMS are airbag deployment chips, right? Accelerometers. I don't know how the ones in a smartphone work, but the same thing that is able to tell you that this thing moved. Also accelerometers, typically with some moving component, and then electrodes to kind of measure how much did it move to figure out how much did it accelerate. So. Yeah, so we actually use MEMS all the time, but yeah. Atomica, who used to be IMT, also between the highway and Hollister in Goleta, is one of the biggest MEMS foundries in the country. So that is their expertise. And they do some really cool chips.
kind of familiar with the old gas lasers where you had the high out, you had your output coupler and your high reflective mirror. What material do they use and how do they make them and polish them? And are they still using? They're still using mirrors in solid state. Right?
Yeah, good question. The question was a typical gas laser is like a fluorescent bulb, but it has two physical mirrors on it to bounce the light back and forth. So how do you do that in solid state? These in a small crystal like this, the crystal actually has a really different refractive index, speed of light, than air. So for the most part, literally when the light hits the edge of your chip, the cut edge of your chip, already about 30% of it reflects, just from that, right? Now you do need that edge to be really smooth and not rough, otherwise the light will kind of go in lots of different directions. So because you're working with crystals, if you've ever cut glass, one of the ways you cut glass is you don't saw all the way through it, you score it and let it break itself. And you've seen what that edge looks like. It's actually really smooth. With a crystal, it's atomically smooth when you do that. So you nick the edge, put some pressure on it, and when it cleaves itself, you have an atomically smooth surface. That's actually the easiest way to make an output mirror for a laser. It gets more sophisticated than that, right? I mean, obviously.
I didn't know, do these literally have mirrors there, or the mirrors are basically
those are the mirrors.
And then you have a certain one that transmits at like 30%.
Yeah, exactly. So I mean, you're right. It gets way more sophisticated than that, right? So a lot of light manipulation happens here. You can add coatings with multiple layers to increase the reflectivity or decrease the reflectivity of that mirror. They do patterning steps in the waveguides that have repeating layers to trap certain wavelengths of light and cause really high reflectivity at certain wavelengths of light. So it does get way more sophisticated than that, but kind of the simple version, like for example, if I was going to make a 50-cent red laser, I'd probably do it this way. I figured out a way to make it work with just cutting it and not doing anything else.
So polishing optics is no longer still needed.
It depends. Sometimes we have to polish these chips. It depends, right? I mean, if you have a single crystal, you just let it do the work for you. If you don't have a single crystal, so there are some chips, photonic chips that, it can be hard. Yeah, so it really depends what you're making. No, actually, you'd be surprised. We still have mechanical polishers with different grits, and we put the chip on there and we polish those down. So no, all that comes from Galileo polishing lenses. We still do that kind of stuff. Yeah, good questions. Any other questions? See, the longer I give you guys to think, the more questions you get. Okay.
What's your motivation out here doing all these speaking events?
My motivation?
Yeah.
I told you my motivation at the start, which is I really want people who live here to ask, how do I do that? Right? What class should I take? Do you have an internship? I want people who live here and just like me will eventually become geeks in this and just want to know more and they can't stop thinking about it. I want them to get these jobs. That's one of my main motivations. So I think we have a lot of people in town who could be making 10, 100 times more money than they're making right now, and they don't know that they would love this and be great at it and make tons of money doing it. That's a good amount of my motivation.
What is the pay range for a senior engineer, 10 years experience?
Okay, a senior engineer, 10 years experience. Okay, I don't want to put words in the mouths of these, but yeah, we're talking 150, 200K, something along those lines. Entry level, we're probably talking like maybe less, maybe it's 110, 120. I know inflation kind of changes things a little bit. But entry level, like someone who, so one thing I started and spearheaded with a number of other colleagues at a couple of companies and at UCSB and at City College, was we started Santa Barbara's first clean room training for people that aren't UCSB undergraduates. UCSB undergraduates already have amazing classes in electrical and mechanical and material engineering degrees for becoming really good at making microchips. And I came here having never ever gone to the clean room and came here for graduate school and learned all this, right, at UCSB. So if you're at UCSB already, you have a great path. Like you're at one of the best schools for learning semiconductors and microchips. But for everybody else that lives in town and is not a UCSB student, they basically had no way of getting into the industry. Companies were constantly headhunting each other. Sometimes it felt like we were all headhunting the same like 10 people. And they could demand any pay they wanted, and they were getting 3 jobs at the same time. So we started with City College, and again, a lot of help from other teammates in town, Santa Barbara's first clean room training for people that are not UCSB students. Using a UCSB facility, because UCSB actually has 3 clean rooms, which is a lot of clean rooms for a university, and partnered with Santa Barbara City College we made this 1 week boot camp for people to just get in there and be in the clean room for 1 week and come out having made two wafers of chips, right? So one is just a cool art wafer. Jacob got to do that as well. Where you just get a picture of you and your mom on the Eiffel Tower, and you print that onto a wafer. And then the second one is actually a real MEMS pressure sensor with a moving membrane and a Wheatstone bridge electrodes on top of it. So
Students get signed up for that, and how much is,
um,
how you get selected?
yeah, good question. Ask me. It's one way. It's not just me. I have a whole other team. My colleague Ben Werner also like really does a lot of outreach. And yeah, what we're trying to find is who are the people that actually want to go work at one of these companies. We're really trying to increase that number of people that want to go learn how to do this and stay in town. If they have family in town, that's even better, right? Because then they have local roots, right? And really help them be able to get into this industry and stay local, so that they become the person with 40 years experience and everybody wishes they could hire. So one way is talk to me and I'll get you in touch with the right people. Right now that's a 1 week boot camp, right? So I used to call it a training, and I realized after 1 week it's more of a boot camp, right? Like you're not an expert in making microchips, but after 1 week, what really I've seen has happened is that you come out of there, you go in there having no idea what a microchip even is, and you come out and you think, okay, yeah, like somebody can make a microchip. I guess you probably have to take 20 years of school to do that. They come out after 1 week going, I can make microchips. That actually wasn't that hard, and I could learn more, and I'm excited about it, and I don't mind the environment. I don't mind the machining environment. I don't mind wearing protective equipment and all that stuff. And that is actually the thing that de-risks the companies the most, right? I can't teach you to make exactly what that company makes because they're the only company in the world that does that, right? Instead, when you come out of this class, you've shown the companies that you are teachable, that you like the environment, that you can learn more, and you can learn their unique process. They now can take this. You're now de-risked for them to be able to take the risk on actually teaching you how to make their process, make their chips. Exactly. So yeah, we've literally seen friends of ours who've gone through the class like bring their your boss said something, you made a mistake, but when you're excited about what you do, this gets you up the next day, like keeps you coming back. So yeah, if you know anyone that's interested in that, or you are interested in that, get in touch with me. I'll help you figure out how to get in there.
You talking to high schools too?
Yeah, right now we're mostly focusing on City College. City College here is effectively doing the vocational training as well. Like you have tons of high schoolers doing dual enrollment for free at City College, so it's kind of the vocational school as well, and they confer associate's degrees, and they handle transfer pathways to other universities. So there's actually a ton of exit points at the City College. So that's kind of the that's where we're focusing. One thing that you find at City College that you don't find as much at the UCs is extremely highly local population, right? So if I want people here to be able to get these jobs, that's where you find the right people in the STEM groups or in the science groups, right? We are sort of using the City College to also sort of be the proxy for local high schoolers that want to figure this out as well. Yes, good question. I will say we just recently, like literally a month ago, got the additional funds to start to build a semiconductor associate's degree at City College, again, using UCSB clean rooms. So in a couple of years, it's a 3-year program. So hopefully at the end of 3 years, we actually have that as well. My goal is that you want to give as many exit pathways as possible to each student, because I don't know what their situation is, right? There's any number of reasons you'll go all the way. They might want to go all the way through a PhD, or they might want to just get a job right away. Whatever they want to do, if they want to get into the industry, I want to help them do it. So the clean room boot camp, the 1 week thing, that'll get you in the door at the entry level right away, right? That's kind of the goal. But I also do hope that you'll also do the associate's degree, and then you really have taken the physics and math classes at City College to say, okay, I really understand this better. if you then also want to transfer to UCSB and really do the engineering pathway, that's even better, right? Then you really know, okay, I actually know how a transistor works. I could design one from scratch. In the classes at UCSB, I literally made them myself and made circuits work, right? I mean, I think we're trying to build the entire workforce pipeline for semiconductors in this area so that people can really choose how far they want to go. Yeah, good questions.
Let's give it up.
Okay, thank you. Thank you. Thanks very much.
Thank you so much.
Yeah, thanks a lot.
Thank you so much.
No problem.
So yeah, thank you all so much for joining us. Next month, one of our members, so you, is going to be giving a talk on Canvas and specifically building autonomous drones using Can Drone. So tune on in. So thank you so much for joining us, and that was absolutely phenomenal. So obvious how passionate you are.
I do
about
love
this,
it, yes.
and I love it. It's great. Thank
Yeah.
you so much.
Thanks a lot. Appreciate it, guys.
Thank you all.
No problem. Yeah, nice to see you here, man. I'm glad you made it.
Thank you very much.
Here you go.